You've definitely experienced the Doppler effect in real life. Imagine a car honking its horn as it approaches you. As it moves toward you, it seems like a honk is really, really high. Then after it passes you, it seems like it gets a lot deeper. We can understand this phenomenon using wavefronts. For a stationary source, the wavefronts look something like this. Now if we start to move that source to the right here, we can see that the wavefronts will actually start to bunch together in front of it and spread out behind it. So if we look at the frequency or rate per time we see a wavefront, in the front of the source as it's moving to the right, we get a higher apparent frequency, and behind it we get a lower frequency. This is why we see the Doppler effect. Now, we can also imagine that the source is standing still, and instead the observer is moving at some speed to the left to try to see it. Well, you'll get the same phenomenon, where you'll hear more wavefronts quickly if you move toward the object, and once you go past it, you'll hear the spread out wavefronts. Mathematically, we can combine all of this information into one neat Doppler equation that relates these speeds and the frequencies we hear. Here, v corresponds to the velocity of sound, which is some constant that depends on temperature and pressure. V observer is the speed of the observer, so if the observer is stationary, this would be 0. V source corresponds to the speed of the source, so if the source is moving, this is where we actually input it. Now, frequency of source is the frequency that the source is putting out when it's stationary. So this is the actual pitch that it's putting out, and if you combine all of these things, you can get the observed frequency that the observer is actually going to experience. Now, we also define Vs and Vo to be positive when the motion is bringing the objects toward each other. This ends up leading to some funky sign conventions in the equation, but we can understand why qualitatively. Let's say the source is moving toward you. This makes Vs positive. Well, we know that as the source moves toward you, the frequency must go up. So we end up subtracting that value to make the denominator smaller, which will make the frequency we observe a lot bigger. Alternatively, if the observer approaches the source and we have a positive V observer, we know the frequency should still increase. Here we use a positive sign so that we add them together, we get a big numerator and therefore a big observed frequency.